it was defining several important parameters of antennas, of which we have learned gradually during the whole semester. We did not have the background completely when we firstly started the chapter 2, that's for sure, at least for some aspects, but that is how the textbook was organized, where it was trying to introduce important concepts by also providing several examples. For example, in chapter 2, there was a strong emphasis in the way into explaining how an antenna is formulated, not formulated, sorry, how the radiation pattern of an antenna can be drawn, can be designed. So with including principles such as directivity, and we talked also about, in chapter 2, it was a discussion about that we could have also antennas that are omnidirectional, so that they can have the radiation pattern spread across all the angles, including phi from 0 to 2 pi, theta from 0 to pi. But next to the omnidirectional antennas, we had also antennas that had a high directivity, which means that they could really point to some predefined direction. Let me have a look for a moment, going over the material. Chapter 2, chapter 3. So chapter 2, it was mostly, actually chapter 2, it was huge piece of material. And I'm trying to find, I have printed the equations or the formulas of chapter 2, but I cannot find them for the moment. That was really a very strong leading factor. Notes. Chapter 2 polarization. So, in fact, in chapter 2, so we talked about radiation pattern, radiation power density, radiation intensity. We talked about the solid angle, and I want you to be I want you to remember what the solid angle means in the spherical coordinate system. Sorry. Found this. So we started with materials from chapter 2, where was the whole chapter. It was about the fundamental parameters of antennas, and this is what we have heard or worked on during the largest part of the semester. So these topics, we talked about these, and other than these list here, we talked about bandwidth, polarization. Polarization is very important, and antenna temperature, Freeze equation. The 217, 218, you might skip these, okay? These two, let's skip these. The rest, it's really which we have seen the activity, maximum effective area. We have the antenna vector effective length, equivalent areas. So these topic 215, 216, we have the antenna radiation efficiency, input impedance. Now, regarding the impedance, we're not going to focus much in the final, okay? So this analysis of, we've solved a couple of examples, but we may not pay a complete focus on this aspect, which is 2.13. But regarding the polarization, this is important. Especially, I want you to be aware of the exercises when we work on the matching of the polarization. For example, we can have an antenna, which is a receiving antenna. It can have a specific polarization. Then we can have an approaching wave, which has a certain polarization. Whenever there is a mismatch in the direction of the polarization directions, then we expect some loss, which is defined as PLF, polarization loss factor. So from here, you could pay less attention to input impedance, 213, 217, and 218. That does not mean that you don't have to read the book regarding these, okay? So these are, we talked about the amplitude, phase, polarization, and the major problems in chapter 2, it has to do actually, and in fact, all of these elements in chapter 2, you should always try to focus a lot on the units that are for the different variables. For example, you can carefully have a look of what is the unit of the pointing vector. Pointing vector, it is a cross product between the electric field component and the magnetic field component. Both should be intensities, which is E and the H. And you should carefully notice what is the unit of that S. So how do we measure it? What is it? Is it watt per meter square or watt per some other unit square? And you should also be careful regarding the specific antennas. For example, they might have a total radiation power which can be measured in the order of watts, okay, or watts. And this, once we know this power, which is measured in watts, it is relatively easy for us, or it's very easy for us to figure out what is the radiation density as a function of distance, which means that if we have, let's say, 10 watts, we can calculate what is radiation density at a distance of 1 meter far away from the antenna. 1 meter is very close, actually, depending also on the order of the wavelength is. But in this case, mathematically speaking, all we would need to do, you would have the total power divided by 4 pi r square. R is equal to 1. You would have the power density equal to whatever the power is divided by 4 pi. If you are to calculate the power density at a distance of 100 meters or 10 to the power 2 meters, you would have to divide. But again, this type of antennas we're discussing, they would be omnidirectional. So they are all distributed, or the radiation pattern, it's pointing around all the possible directions. But you should be careful regarding the units or the quantities that you are offered. So we have the radiation power. We have also the radiation intensity. And the radiation intensity, it is this factor which is equal to U. And there is a general relationship between the W and the U, which is the W, as we called it here in the class. Maybe it's good if we move a little faster. So here we see some examples of how the radiation intensity changes as a function of N and the wavelength. Of course, this kind of information in this slide, which is slide 12 of chapter 2, this is pretty premature because the antennas with several components, we covered these in chapter 6, I believe. Okay, so this is really some piece of information which is very early to be presented in chapter 2, but as we said, it is a comprehensive chapter covering a lot of material. We have also the definitions of lobes. What is a minor lobe in an antenna, side lobe, back lobe. This is how we can also see from here what could be the definition of the lobes in a radiation intensity. Okay. So we said that in the class or in Google Classroom, we have shared also some MATLAB codes, which you can run them or implement them and try to draw the radiation patterns of several antenna components on your own. So here there are the codes. When we were discussing chapter 2, we just went over these. Okay, then after the MATLAB section, here we talk about the radiation patterns of a specific antenna. And here, let me see for a moment. We have the principal E plane. So this is the theoretical aspect of how the polarization can be defined for a specific antenna. Principal H plane, isotropic radiator. Isotropic radiator will be an antenna which has equal radiation everywhere. It doesn't have major lobes and minor lobes, but assuming that it has an equal radiation, how can we call it? Radiation density as a function of theta and as a function of angle phi. Okay, so here we have omnidirectional patterns. This is an omnidirectional antenna, so everywhere we have the relevant fields. And what is essential or important is also the fact that the electric field in the far radiation zone, it is expressed as A theta, and the magnetic field is described as A phi. Now, this can also be expected from most of us, also because of the fact that, but let's notice actually, what is the current here? The current, actually, we're not shown, we are not told what is the type of the antenna here, because if it was offered, we could then calculate actually how the electric field and the magnetic field propagates. But what is essential here is that if we have a electric field which has a direction of A theta and the magnetic field which is H phi in spherical coordinate system, we know that the cross product between the E and the H is going to give the S vector, which is the pointing vector. And we know that the pointing vector is always going to point far away from the antenna. So if we have here the antenna, the pointing vector is going to be like this, and the electric field vector is going to look something like this. This is E theta, and this would be H phi. And we care that E theta times H phi, the directions of these would give the pointing vector. And often from an antenna, we would expect this would be the vector S, and then the E and the H can be considered as two vectors which are tangent at a spherical shape. Okay, so at the distance where we want to calculate the relevant parameters, let's assume we have a sphere with that radius. We just draw two components which are tangent to this outer surface of the sphere, and we can draw the E and the H principal patterns of the radiation. Then we discussed about an important concept, which was the field region. So we had the reactive field region and also the radiating near field and the radiating far field. There is always a kind of jokes among the antenna designers where they say that the dangerous component is always the radiation part, but the radiation part is never in the proximity of the antenna. So what is the harm atë bëndëm antena kur je shumë larg apo kur je shumë afër? Shpesh parashtrohet çështja që antena ka më shumë dëm në distancë vetëm se ka emrin radiation zone, por kjo nuk është e vërtetë. Patjetër, even if you are in the proximity of the antenna in the reactive near field region, still there is quite some side effects that can be caused on users, let me call it this way. And these far field regions, this would be the Fresnel and the Fraunhofer region, where the reactive near field, where the phases are near quadrature, so they are real highly reactive wave impedance. So this is the near field is actually like a zone which has a very high impedance. So this can even considered as a circuit which has a specific delay. So it's really something like having an inductor connected to a source. But the radiating near field, we don't have these issues. There is also an aspect that the field components in the reactive near field, they are changing much faster than in the radiating near field. Sorry, reactive near field, the fields decrease much faster than the radiating near field. For example, they decrease too fast, and the decrease is often, sometimes it is 1/r². So if we are in the proximity of the antenna, the fields around here, they can change as r⁻², but if you get further, the decrease can be as r⁻⁻1. Pra, gradienti in izvoglimit është më i madh këtu, atje që të fush është më e vogël. Dakor? Por gradienti bie në mënyrë më graduale. We have far field. So here there are the regions where which would be the far field and the near field. And what we understand also from here is that the major lobes and the minor lobes that are created at some distance from the antenna, they are created mainly at a very far difference. And actually, one fact here is also because of the diffraction, not diffraction, the constructive and destructive interference. So we can have constructive and the diffractive interference. Which can happen at a far distance from the antenna. So that's why in the far region, which is the Fraunhofer, what we can see from this slide, we notice that there are some minor how do you call this? Some nulls, which are pretty clear, okay? And the nulls are often created just in the middle of two lobes of similar intensity. Okay, so here we have again some the drawing of how the radiation power pattern looks like. And during the course, we have also added this fact that often, whatever we measure for an antenna, it is often the approximation, because the clear null region for an antenna, it is often just a mathematical apparatus, but it is hardly true for a real antenna. So we always have huge approximations in all possible cases for antennas. Ndërkohë, nëse japim 5 minutë pushim, do kalojmë te klasa ku kemi klasë të lirë që është A129, kush është në shkollë, mund të kalojmë ngadalë te A129, edhe në atje do kaloj. Por ndërkohë të vazhdojmë. Atëherë kemi ky është kapitulli i dytë. Ky është thjesht një element që na kujton, this is just an element which reminds us of the solid angle. So the solid angle is this d omega, which is equal to r squared sin theta, d theta, d phi. So it's something like a small revision of how the spherical coordinate system can be defined. So let's see what we have here. For sphere radius r, find the solid angle theta in square radians per radian for a spherical cap. And here we are given the angle theta from 0 to 30, phi from 0 to 36. So apparently what this is looking for, it is in fact looking for the angle which can be defined. Let's think about for a moment about the planet Earth. Planet Earth, we're trying to find the angle, but when you say the angle, if it is an angle on a plane or on a piece of paper, ky matet me radian ose me këndin theta. But now we want to define a plane which is is going to look something like this. So for example, in order to increase the resolution of the object that you are seeing, so often when people get very old, in order to get a higher contrast image, what they can do is that they can make a very small hole with your finger, and you can look through this. You can really increase the resolution. Or a better technique is just you take a piece of paper, take a needle, merr një gjilpër, bëj një vrim kësaj një copë letre ose që është komplet e zezë, edhe shiko përmes kësaj, do shikojmë që do të ketë një rezolucion shumë të madh. Ndërkohë që kemi një vrim e cila është një vrim piksore, ajo që shikon syri dhe që hapet me si funksion e distancës, ai përkufizohet solid angle. Dhe tani këtu në këtë moment ne kërkohet solid angle kur kemi këndin theta nga 0 deri 30. Çfarë është nga 0 deri 30? Është nga poli veriut deri në paralelin 60 gradë, dhe 60 gradë që matet nga ekuatori normalisht, po ne që po marrim lëndën e antenave, këndin theta e masim nga poli veriut, që do thotë zbresim 30 gradë 30 gradë mund të jetë diku deri në Danimark. Pra, po të jemi në qendrën e tokës, ne na duhet që të identifikojmë sa është solid angle që shpaloset nga zona që është plus 30 gradë, minus 30 gradë with respect to z, ose 0 deri në 30, po ndërkohë që kemi këndin fit 360 gradë. Po duhem të shikojmë këndvështrimin nga 0 deri në 360 gradë është gjithë rrotullimi rreth rrotull planetit Tokë. Kur vim këtu te integrali, po shikojmë solid angle do të jetë barabartë me sin theta d theta dhe integralin e delta fis. Po ta shikojmë këtu, neve na del që nga integrali gjem diçka që është 2pi është 6.6. 6/10 0.6. 70-30% 0.83. Pra këto steradianët janë, si ta themi, janë deri diku, janë radian në katror. Pra është ekuivalente si kur gjejmë sipërfaqen e cila është dx do y, ajo është metër her metër del metër në katror, kurse solid angle që kemi ne këtu, që do thotë beam solid angle, mund ta konsideroni sigurisht radian në katror, e thamë këtë pjesën në fakt. Dhe quhet radian për radian katror sepse delta phi matet me radian, delta theta matet me radian dhe po integrojmë mbi dy komponent. Okay, radiation radiation power and radiation intensity. Këtu kemi W, which is equal to the cross product between the E and the H. At the same time, here we here we see that there's a similarity between the antenna and the radiation power, which is written as an equivalent potential and an equivalent current in the antenna. So here we have the power, and actually when we look for the power is measured in joule per second or watt, and we notice here that the pointing vector, it has a unit of watt per meter square. Okay. Yeah, this is watt per meter square. That means that the radiation intensity U, it has units of watt, because radiation intensity, which this is where we have it, this one is W times the unit solid angle, divided by that. But the radiation density is watt per meter square, multiplying by R square, we get the U. So U, to some degree, it is often a constant value. It does not, let's say it this way, it does not change as a function of R, okay? Pra nuk varet nga R-ja. Okay, so now, if you like, we can have a very short break